Okay, so the next thing we'll do, we'll wrap up 1.1, a kind of generic discussion of functions. The first couple things are pretty straightforward. Couple definitions. So let me put the definition down. DEF definition. So a function, F, we'll call it, is what we call increasing. On an interval we'll call I. We'll talk about that in a second. If, and this seems more technical than it needs to be, but there's a point that I want to make. If a bigger x value, which would be to the right of the first one, means that the function is of greater value. So let's do this. This is our friend from 1.2. Got it that time. The absolute value function. So this would be increasing here. Right, as x increases, as you go this way in x, you go this way in f of x. So this would be increasing on what we'd call the interval 0 to infinity. Oh, sorry. And it's pretty self-explanatory. We read left to right, so as you're going left to right, you're going uphill, you're increasing. The point to be made, though, is this. This is interval behavior. It's kind of sloppy to say it's increasing, say, at that point. That's sloppy. Instead we talk about the function increasing on an interval. This function is increasing from 0 to infinity, and this will come into play. Chapter 3, we're going to do a lot of this. So what comes next? No surprise. A function. Oh, I should just add for completeness. On that interval. It's increasing on that interval if this occurs on that interval. Okay? Is decreasing on an interval I. Different interval, of course, but it's just a definition. If, and now as we move to the right, what's happening to the y values or the f of x values is going down. And again, on I. So again, this is no surprise, right? This would be decreasing over here, and if we were going to, again, describe the behavior on this interval, this is decreasing from negative infinity to 0. Okay, no big deal. So you'll see some of this stuff in the homework. Okay, a couple other terms. Okay. Okay. So this is not interval behavior. This is global behavior. These terms you state about a function in its entirety. Definition. A function f is what we call even if, and this will seem a little strange, but it's okay, f of negative x equals f of x. So let's think about what that means graphically, because that's a point that we want to make here. So the idea is, say I pick some x, over here. In fact, I'll just call that x. Just call it x1, whatever. Well, let's say the y value f of x1 is here. Well, what is this telling me? If I have the negative x1, which would be the mirror image over here, I have the same y value. And this is the case over the entire line. So what you have, and this is just an example, I missed that one. You have what we call y-axis symmetry. Okay, it's a mirror image in this direction. In the parabola, this is sort of a parabola. That's a good example of it. Okay? Similar. A function f is what we call odd if f of negative x equals, not f of x this time, negative f of x. Well, what would that look like? Again, I'll pick some x, call it x1. Again, I'll just make it kind of like the one above it. So that point is here. Well, now what I'm going to say is the mirror image of this x value over here is not up here. It's negative f of x1. So that would be here. And if I take all these points, what I'm now doing is sort of a double mirror. We call this origin symmetry. I'm going to take the points, I'm going to flip them over, and then I'm going to flip them over again. So a good example of that, if I can sketch it nice, is the cubic. Right? If I took this piece, or this half from here out, and I flip it this way, and then flip it this way, we have this graph. And this is, we refer to this as origin symmetry. So a couple things. Number one is a lot of functions don't have any symmetry. So if asked, is the function odd or even, it's very common to say neither one. And if asked, is a given function odd or even, how would we do that? How would we tell? Well, we don't have a graph, let's say, and even the graph isn't a guarantee. But what you'll notice is for both of these conditions, the left-hand side is the same. The left-hand side is f of negative x. So what we'll do is, given a function f, if you're given f of x, then we're going to say, well, what's f of negative x? I'm going to just put negative x into the function and see what it is, and if it's either one of these, the original or the negative of the original, I've answered the question. So let's see an example or two. So that's the good news, is you check them, you kind of check both of them at once. So let me find something here. Yeah, I'll make one up. So the question is odd or even or odd, or neither. So a simple example would be, okay, this is the original. So is this function odd or even? So what I'm going to do is, again, I'm going to put in negative x as the input. And when you do this, it's smart to use parentheses. So I'm going to use the input negative x. This is going to be squared. Now what happens when I square negative x? Negative x times negative x is x squared, and the negatives go away, right? So this is equal to this. And what's this? This is f of x. So f of negative x equals f of x. That is the condition, that is the definition of being even. Let's see. These are same question. Call this one G. Okay, so now I'm interested, what's G of negative x? And again, I'll use parentheses. Okay, now the one on top there is just to the first power. So those essentially just get dropped. I have the same thing happening here. And this negative, even though it's associated with the numerator, could just as well be stuck out front, right? So what do I have here? I have the exact negative of the original. So this is negative g of x. So this is the condition for odd. Okay, so again, most of real functions of, interesting functions are neither. Okay. Okay, now we'll move into something. Sometimes this is a little confusing for students, but we'll work through it. And that is a specific sort of form of a function, and this is called piecewise. Piecewise functions. So, what is a piecewise function? And this is something that's nice to see examples of, but I'll put a definition down. A function, there's a car alarm going off. That's definition. In other words, the right-hand side, right? F of x equals, that's the definition. A function, that's definition, depends on the value of the input. So let's see what one of these might look like. Example. Use f of x equals, and then usually you see some kind of curly bracket like this. And let's say it equals, x plus 1 if x is less than 1. X plus 2 if x is greater or equal to 1. So this is what there's two different definitions of the function. Which one you use depends on where x go, which condition is met. X is either less than 1 or greater than or equal to 1. It's one or the other. So you have f of, say, 4, which condition is met? The first condition. 4 is greater than 1. So if that's the case, I use this definition. So it'll be 4 plus 1. Likewise, whoops. Sorry, that's not correct. This is greater than, my bad. 4 is greater than 1. I'm using this one. I had it backwards. So it'll be 4 plus 2. Sorry. What about 0? What if I have f of 0? Well, 0 is less than 1, so that's the top condition. So this would be 0 plus 1 equals 1. So the evaluation shouldn't be a big deal. What sometimes people struggle with a little bit is the graphing part of this. So if I wanted to graph this, there's different approaches, but here's how I'm going to do it. Number one is you need to know what the pieces look like, right? And that's why I did the essential functions first. If you don't know what the pieces look like, you have no chance. Now, I expect these are lines in y equals mx plus b form. You're expected to be able to do that. But one thing you want to do is come up here and look at the conditions and identify where the transition happens. The transition happens here at 1. So I'm going to add this as well. I'm just going to put a couple tick marks here just to help me out. Maybe a couple down here. I don't know. But what I'm saying is, in this definition, if x is greater than or equal to 1. So in other words, from here out, I'm using this definition. And that's a line of slope 1, y-intercept 2. So if I were to draw that line in its entirety, it would look like this, right? But it's going to start here, right? This would be the y-intercept. That's not part of it. The next one over is 1 up because the slope is 1. So I go 1 over, and then this is the piece. This is the bottom piece, this piece. Now what if x is less than 1? That's to the left of this tick mark. That'll be this line, y-intercept 1, slope 1. So that looks like this. And now here's a key part of this. When I did this piece, notice I ended with a solid dot. And that's because of this symbol. Greater than, which is the line, or equal to, that's the dot. That's not the case with this piece. For this piece, we define it with this line up to 1. But when I get to this tick mark, what do? Do I just end? Now, instead, what we're going to do is we're going to put an open circle there just to show, that shows that it's up to, but not including that point. I couldn't have a solid dot there. It would violate the vertical line test, right? So this is what I'll do. Some people will do this, which is fine if you're just careful. They'll graph both pieces, and then they'll erase what needs to be erased. They'd erase this and erase that and add the dots. The dots have to be there. Okay? Let's see another one. Now, there's nothing that says it has to be 2 pieces. It could be 52 pieces. So let's just change the name. And we'll say this is x if x is less than -2, x squared if, and let's say -2, so if x is, I need to have, let's make this less than or equal to. And let's, four, if x is greater than 2. Get all that down. Oh, let's do this. So we have x less than or equal to -2, x squared if it's between -2 and 2, 4 if x is greater than 2. Okay, so again, I'm going to just locate my transitions. My transitions here are at -2 and 2. So it doesn't really matter which one you start with. I'm just going to work left to right. So that's top to bottom in this case. So if x is less than or equal to -2, which is from this tick mark to the left, I'm going to have my vanilla line aimed right at the origin and a solid dot, because that's inclusive. Now between these, but not including these tick marks in this interval, I'm the parabola. So it's going to be, this shape. We know what the shape is. And I'm going to have hollow dots at the end. But where do those hollow dots go? So I'll put these values in there. -2 would be 4. But I'm just up to, but not including that. And the same thing over here. And that's because this is what you call a strict inequality. I'm not including these two values, so I don't include these two dots. Now, if x is at the tick mark or to the right, this is a constant function of 4. So I'm actually going to now fill that in because of this piece. So that dot is associated with this piece, but it doesn't really matter. Excuse me. And I'm going to use a word now, just kind of foreshadowing what's going to come later, but this is what we call continuous. Okay, there's no break here. This is what we will call a discontinuity. There's a break in the action. This comes to this dot, and then as we move forward along x, we're going to ride this part of the curve. Okay, so an important extension of piecewise function is this, and this is something that's often misunderstood. I'm going to go back to the old absolute value function. And students are taught things like, I don't know. They're taught things like, oh, you make it positive. Whatever's in there, you make it positive. And that's true. That's not untrue, and that's fine if you're working with numbers. Absolute value of 5 is -5. Or back, sorry. Absolute value of -5 is 5. But if you're working with functions, with variables, that is a little bit too crude. So the precise definition, and this is a definition, of the absolute value is this. Absolute value of something equals, and this is actually a piecewise function, it equals whatever it is if it's non-negative. In other words, you just drop the absolute values. Well, if what's in there happens to be negative, we're going to negate that, and that makes it positive. Now, this might sound like I'm just making the just make it positive thing too complicated, but again, you kind of have to use this approach when it comes to functions. So let me do this example. We're going to graph f of x equals x minus absolute x. So if I just go about the whole, well, -5 is 5, you go about that whole philosophy. This isn't, I don't know how you do this. So what we're going to do instead, this contains an absolute value, so we're going to use this. We're going to rewrite this as a piecewise function because the absolute value function is a piecewise function. So what's the condition? Well, this will be, so again, what's in here, this is a, this is x. So I'm going to say if x is greater or equal to 0, that's replacing this, or if x is less than 0. This could be 2x. In fact, we'll leave it at this for now. Okay, so what is this? What are we saying again? If what's in there, which happens to be x, if that is greater than or equal to 0, we leave it alone. We leave it as what it is. So in that case, this will become x. X minus x is 0. If what's in there, which is x, is less than 0, then we negate it. So this becomes negative x. x minus negative x is 2x. And now this is an easy thing to graph. So this will be 2x, which kind of looks like this. And then we hit the origin, and this is going to be a little hard to sketch. Now it's just 0, so it's this. How does that look? All right. Nope, sorry. So embrace this. It might seem like we're making something more complicated than it needs to be, but this is important to understand. This comes up now and again, and it's in the homework. So look forward to seeing you on Wednesday, bright and early. I didn't make the schedule, trust me.